So today we're taking a look at the 5.4 and the 5.5 material, both of which are working with applications of linear systems, meaning story problems. Now the main types of problems that we're going to be seeing between both of these sections are equations that we are going to need to know, are ones we have here. Some of them look like a total cost equation where we have, here's our total cost. It's equal to a variable cost of some kind. Maybe it's dollars, how much money we make per hour, like an hourly wage or something like that, or commission, or similar to some of these other problems that we've seen, plus a fixed cost. Maybe it's you are going to get a certain amount of money guaranteed just for working at some place, something like that. So a variable cost plus a fixed cost. We might also have our distance is equal to rate times time, aka our DIRT problem showing up for us. So again, this could make a return. Mixture problems, also known as bucket problems, is just one of the ways you can organize it for yourselves. So the rate of concentration of something multiplied by the amount of mixture that we have in total. Again, we'll see some examples of a couple of these problems down below here. These are all problems that we have at least seen once or twice before this in previous chapters. We also have some other ones known as the rate principle. This is kind of a generalization from our distance is equal to rate times time problem. So we have an amount of something is equal to a rate times a base. So this is generally for something the effect of, by comparison with our distance problem, this is a distance times a rate times a time. The rate principle could be, let's say it's how many boxes we're able to move from one room to another at a certain rate. Maybe that's by time, maybe that's by days, maybe it's by a different kind of a calculation, but we have an amount is equal to a rate times a base. This is the generalized version of what the distance formula looks like. So we're going to be seeing this show up quite a bit, I think, in this section. That's why I made the note of this one here. Again, this is extraordinarily generalized, not very specific, because of the fact that we can define what the amount, the rate, and the base are in a lot of different instances. And then we have GPA problems. So how we determine the GPA of someone. And we determine that by adding up the sum of the grade points that someone earned, and we divide it by the sum of the credit hours that someone has taken. It can also be written as sigma grade points over sigma credits. The sigma is used to denote the sum of. Just do that with one symbol versus sum of written in there. So we add that amount together, we divide it by the total number of credits, and we're going to get our total GPA as well. And we're going to see an example of this later on in our notes as well. So we will be able to see what this is actually going to look like. Now, a strategy that I would recommend for story problems, and again, I've mentioned this with a couple other sections in the past, but I do want to at least say it again. There is no universal, here is how you solve every single story problem that you will come across method. It does not exist. I wish I could give you guys one, but it's not out there. So I've tried making this one to be kind of as best a generalized method that I can recommend for you. This is not a universal, method of this will always work for you. I think it's pretty solid, but it will not work for maybe the same strategy that we used in problem 1 is not going to work for problem 2, which might not work in problem 3, and so on and so forth. So you need to be able and willing to adapt this method and this process to yourself and to the problem that we are working with based on what we have been given. Again, our first step that I recommend with all these story problems, read, reread, and reread the problem over and over again. Repeat this as necessary throughout the entire process. A lot of people with these story problems, and we're going to see that they're not going to be easy. There's a lot that's going on with them. A lot of people just say, okay, I've read the problem once, I'm just going to write something down, and I'm just going to start solving that something because I don't want to look into it more. You absolutely need to be rereading the process or rereading the problem for yourself. Do not just read it once and say, okay, well, I've got everything, I'm done. Maybe that's you and you can do that. If that's you, fantastic. Good for you. You're ahead of where I was when I was learning all of this stuff for the first time. If you are not in that boat, you're like most people with these story problems, which is you need to do and reread this multiple times. There's nothing wrong with that. My recommendation, if you're going through this, each time you read the problem, determine if at least one piece of information is relevant or not to what you're going to solve for. Is this number going to be useful? Is this not going to be useful? Can I cross it out? Should I circle it? Should I, anything like that? Something that's going to help you go, every time I'm reading this, I'm making at least a little bit of progress towards making an equation, determining what numbers I will or will not be using, something like that. Once we've identified some relevant or irrelevant information, identify specifically the useful information for the problem. I would label some variables and some numbers for yourself accordingly, and clearly define what you are solving for. A lot of people will see these and go, well, maybe I'm working with dollars, I'm working with hours that are worked, I'm working with total amount of money that I made, working with fixed amount of money that I'm making, but I don't know what I am solving for in this problem. And a lot of people will just, once again, start writing stuff down just to write it down. Clearly define for yourself, what are you looking for this problem? It goes for all of these. I recommend for step 3, draw a sketch or draw a picture of the situation and label it with the information that you found from step 2. If I know I'm going to use maybe the hourly rate or one of the hourly rates that have been given to us, maybe label that for yourself. This $10.50, that number is an hourly rate. That number is, maybe it ends up being the bonus that someone gets at the end of the day. It's a fixed price, something like that. Label that information for yourself. And I would recommend, if you're drawing a picture or anything like that, write this stuff out for yourself. You do not want to be trying to keep track of, in my head, okay, this is relevant information, and this is relevant information, and this is irrelevant information, and this number represents something, and that number represents something else, and a variable represents, I think this variable represents something, and that variable represents something. Hopefully just in me describing that right there, and you trying to follow it, it's not easy. There's a lot that can be going on with these problems. Let your paper, wherever you're writing on, maybe it's a whiteboard, let that hold this information for you. Do not try and keep track of what is and isn't irrelevant, what's going on in the problem, the labeling of things, what to do next, where you're currently at, what strategy. Don't try and do all of that in your head. It's not easy. It's very, very difficult. So write that out on your paper, write that out on a whiteboard, scratch paper nearby it, something like that. Write it out, draw it on a picture, something like that as you're going through this process. Set up and adjust equations accordingly. As we're seeing up at the top here, and we've worked with this in the past, maybe we're going to use the DIRT problem, the distance equals rate times time. Okay, well, if we're going to be using that, write out the general equation. Nothing says we can't modify that later on, but again, the last thing you want to be doing is trying to keep track of, what equation am I using, which pieces of information are relevant, where would they plug into this equation, am I working with one situation, two situations? Again, as I'm describing this, it seems a little bit overwhelming as I'm going through some of these examples just off the cuff, and you're saying, it's hard to keep track of all of this. Exactly. So don't try and keep track of all of it in your head. Write things out for yourself. Erase them if need be. Put a line through them saying, okay, I thought this would work, this didn't work. Write this out for yourself so you can free up your brain to actually think on and figure out what you can do with all of these things. So setting up and adjusting equations is not something that's terrible to do. Start with your DIRT equation. Maybe the rate is a given number and you put it in accidentally for the distance. Maybe you accidentally put it in for time. Adjust it accordingly. But again, if you need to, go back and read and reread the problem to see if numbers are fitting into your equation or equations as they need to. Once you have a solid setup and solid set of equations as necessary, then you're actually going to solve them. So there is a lot of prep work that goes into setting these things up before you actually solve the system of equations that you are working with. And in some instances, we might not have systems of equations showing up. We might just have one equation. Sometimes it's one, sometimes it's two. Again, it's dependent on what problem we have been given. But all of these setup steps, and it only looks like, okay, it's only 4. That's not too bad out of the 6. These are vital. Cannot emphasize going through and taking your time, being extraordinarily methodical in doing these setup steps. A lot of people rush this, they get wrong equations, and they correctly solve wrong equations. And they still get wrong answers though, because it's not the answer to the problem. And then last but not least, check if the answer or answers that you get are reasonable. If I'm being asked to determine, let's say, what distance did someone travel after they had a certain rate or a certain time, and you get, well, the distance they traveled is negative some number. Is that reasonable in the context of the problem? Can I travel a negative distance? And no, we can't. So something went wrong on either our setup, how we solved this thing, the equation that we set up for ourselves, maybe the picture that we drew was incorrect, maybe we've identified wrong information. Slowly backtrack and see what we got or where error showed up in. Okay? But again, this is not the universal only method that we have to solve these things. This is, as best I could find, a generalized method for solving story problems. You do not have to follow this exactly. You can modify this method or your own methods as you need to solve these problems. But I think most of these are some universal, I would say, truths is the exact correct word to use for it, but some very good universal steps to take whenever you're solving these story problems. Okay. But again, you will need to kind of get through and develop your own process. This is just hopefully a good starting point to go with for a lot of these. So let's dive into a couple of these story problems now. Again, we've got 4 ready to go here. We'll get through as many as we can today. And if we need to go through more of them maybe tomorrow, then we'll do that. So taking a look at our first problem that we have here. So we have Dr. Cox orders a dosage of 40 milliliters of a 16% saline for a patient. Since JD doesn't know how to do his job well yet, he panics and grabs a bag of 20% saline and another of 4% saline, not knowing what to do with them. In a fit of rage, Dr. Cox fumes off to solve the problem for himself. How much of the 20% saline and 4% saline does Dr. Cox need to mix to get the correct dosage for the patient? So again, we have a lot that's going on in here. We need to try and pick out the information that is relevant and irrelevant to what we are going and solving for. I'm going to try and move us up here, so we're going to bring our strategy into light here a little bit for us as well. So we've read the problem once, okay? Our second step, identify useful information, and if nothing else, define what we are solving for. Maybe each time we read this thing, let's figure out what we need, what we are and aren't solving for with this problem. So how much of 20% saline, how much 4% saline does Dr. Cox need to mix to get the correct dosage for the patient? So what are we solving for? How much 20% saline and how much 4% saline are we going to have in total? Or I guess for each of these. We know we're going to have a 20% amount, we're going to have a 4% amount, and we know that the dosage that was ordered is 40 total milliliters. So we have some unknown amounts, we have a total amount that we're going to need, and we have some percentages, some information regarding each of our different things that we're working with total. We're told at the very beginning, Dr. Cox orders a 40 milliliter dosage of 40 milliliters of 16% saline for a patient. So I have the desired percentage or concentration that I want at the very end as well. So I have the total amount, and its concentration all at the same time. We have some relevant information, some relevant numbers. Let's start putting this into a picture or a sketch for ourselves and start applying these numbers in here. This is actually going to be a mixture problem. And we're going to use, in this case, I'm going to use the bucket method that we had from, I believe this was chapter 3 that we use this. We're bringing it back here for these problems. So I'm jumping this over to our Blackboard, but I'm referencing this first example when we're over there. Oops. Come on. There we go. So first example. So again, we have some amount of something mixed with some amount of something else is going to give us our result here. So again, if we have a mixture problem, I have something mixing with something else, giving me a result. If you are using the bucket method, or frankly, even if you're going to use the table method for organize this for yourself, do not put a single number inside the buckets. Do not put a single number below the buckets until you have labeled everything. We'll do this in a different color here. What each bucket represents, and then what the numbers inside the bucket represents and what the numbers below the buckets represents. If you start just throwing numbers in there without labels, this becomes, at least I think, extraordinarily more difficult. So label everything so you know what every single part and every single number is going to represent in our picture. Because if you have to guess at it, that's not good. It's not a good position to be in. So let's start labeling this. So our last bucket, as we went through originally, is pretty much always going to be our result. You could also think of this as the total if need be. So we have something plus mixed with something else is going to give us our result. Now we need to label for ourselves what is the first thing or first bucket that we are mixing together. In this instance, we have a 20% saline solution and a 4% saline solution. So which one do we want to be the first? Which one do we want to be the second? I'm going to say arbitrarily the 20% saline is going to be the first one. So 20% saline bag, and then the 4% saline bag. So that's just how we know, okay, so some amount of the 20% bag, some amount of the 4% bag is going to give us a result. Now we need to label off to the side of these what is going to be represented inside the bucket and what is going to be represented below the bucket. So I'm choosing to have inside the bucket represent the amount of each thing that I'm working with. More specifically, what is that amount being measured in? Is it in gallons? Is it in liters? Is it in quarts? The problem has told us Dr. Cox orders a dosage of 40 milliliters. So what is this amount going to be in? It's going to be in milliliters. Label the units you are working with as well. Again, as specific as you can be with all this information, you need to list that in there for yourself. Now, what are we putting in below the buckets? Well, we have an amount of something. We also need to determine what is the concentration of what we are working with here. And more specifically, we're working with, we have a bag of something, we have a bag of something else. What percentage of that bag is the thing that we are looking for? So I'm going to write in below this, I'm going to write what's the concentration of that bag, meaning what is the percent that is that bag that is saline. Specifically, percent that is saline. And I say we need to be specific on this because I could give you an instance where maybe the first bag is 20% saline and 80% some other thing, some other compounds, mixtures, whatever it may be. Maybe the second bag is 4% saline and then 96% something else. We are specifically looking for the percentage of these things that is saline, not percent that's water, not percent that is maybe ibuprofen or some other mixture or something else that could be in there. We are specifically tracking what percentage in each of these bags is saline. So again, as specific as you can be with what each part represents, what amount are we looking for, what percentage of something are we looking for, all of that. And now we can start filling in parts of this visual that we have for ourselves. So again, rereading the problem, Dr. Cox orders a dosage of 40 milliliters of a 16% saline for a patient. Okay, so we know our result. We know that we want to have an amount of 40 milliliters. We also know that the dosage, the amount that we want that thing to be a total of 16% saline. Again, think of it as what's the resulting thing? The resulting thing, 40 milliliters, 16% saline. Okay. So we're told then, since JD doesn't know how to do his job, he panics and grabs a bag of 20% saline and another with 4% saline, not knowing what to do with them. In a fit of rage, Dr. Cox fumes off to solve the problem for himself. Okay, so that sentence is irrelevant. How much of the 20% saline and 4% saline does Dr. Cox need to mix to get the correct dosage for the patient? So in the amount of the 20% saline bag, do we know what that number is? And no, we do not. So we can list that as one of our unknowns. You could use A, B, M, N, X, Y, whatever it may be. I'm going to use X to represent that. So what amount in milliliters of the 20% saline bag do we use? We don't know. We also don't know how much of the 4% saline bag that we're using based on that last sentence. We don't know those two numbers. That's fine. We're being asked how much of the 20% and 4% saline solutions does Dr. Cox need to mix to get the desired dosage? So again, that's what we're solving for. So fantastic. Those are unknowns. That makes sense in the context of this problem. Now for each of these, okay, great. We have these. Now we have these bottom two parts to fill in accordingly. So within the 20% saline bag, what percentage of that saline bag is saline? As it's been given to us, it's going to be 20%. And what about for the 4% saline bag? What percentage of that is saline? Well, it's 4%. We can list that there as well. So now we have everything written out in a nice visual for ourselves. Now we can start looking at, okay, can I create some equations out of this thing? We have two unknowns. We have an X and a Y. So for the number of unknowns we have, we need at least that many equations to be able to solve this thing. So I have two unknowns, which means I need to create two equations out of this visual that I'm working with. So let's start making some. I have some amount of the 20% bag plus some amount of the 4% bag is going to give me a total of 40 milliliters. Again, I don't know what X and Y are, but I know that if I add those two amounts together, I'm going to get a total amount of 40. So that's one of my equations. Better X here. There we go. So I have an equation based on my amounts that I'm working with. Now we could also find an equation based on the concentration of what we are working with. So this is one where we're going to have, this is kind of one of the weirder ones that show up and where it's a little bit different for our What am I thinking on? Compared to our dollars and cents and our mixing coins together. So we have a slight difference here. Now we want, of our 40 milliliters total, we want 16% of that to be saline. So we need to determine if I mixed this concentration plus this concentration, I should get this as my concentration. So the way we're going to go about doing this, we need to multiply the percent of our first bag that is saline plus the percent of our second bag that is saline is going to give us what percent of our final result should be saline in milliliters. So what that's going to look like, I need to first rewrite my percentages into decimals before I do that. So percent to decimals. Those that we have there. So now I know 20% of the first bag plus 4% of the second bag is going to give me 16% of the final result as saline. So basically what our first part here is telling me 20% of the milliliters that I have from my first bag plus 0.4 or 4% of my second bag of saline is going to give me whatever 0.16 or 16% of my final bag is going to be saline. So essentially we're mixing specifically saline amounts together to get our total amount of saline for this problem. And that's going to be our second equation. So this is where this is going to, these problems, or this one specifically, is going to differ from the other mixture problems that we did in chapter 3, where we're working with an amount of something versus a concentration of something, which is what we have here. So we have some differences. But now I have two equations for my two unknowns. And now I can go through and I can solve this thing accordingly. At this point in time, the problem does not list for us, solve this using the elimination method or solve this using the substitution method. At this point in time, it does not matter which of those two methods you would like to use to solve this problem. Either one works. You just have to choose one and move forward with it. Okay? So I am going to choose to use the substitution method, mostly because I have decimals showing up and I feel like those are really gross to use. So using the substitution method, I'm going to solve my first equation for y. I'm just arbitrarily choosing y. You could choose x if you wanted to. I'm going to plug that in for y in my second equation. I'm going to go through and solve this thing accordingly. So in my second equation, I'm just writing out the general equation first. And now I'm substituting values in. Got a better 4 there. There we go. So from here, now we can go through and we've just got a mechanical problem. We're solving this thing for x. So this 0.04 is going to distribute through on the left-hand side. 0.04 times 40. Doing that off screen, just multiplying that together in a calculator. Whoops, should be plus 0.6. And then 0.16 times 40. So going to give me 6.4. I'm combining like terms on the left-hand side of my equation. I have two x terms that are adding together, or I guess subtracting together. So I have 0.2 minus 0.04. So I'm getting that there. And now from here, again, I'm still solving for x. I've got decimals showing up. They're gross. They're terrible. But again, we've got a calculator to help us out with it. So I'm going to subtract 1.6 from both sides. So 6.4 minus 1.6. Again, I'm using my calculator off screen to find these values. You are more than welcome to do that for yourself as well. And then last but not least, I need to get rid of that 0.16. So I'm dividing both sides by 0.16. I'm getting an x value of 30. Now, looking at our problem, what does our x value represent in the context of this problem? So we can go back up here to our picture. And x represents the amount of the 20% saline bag that we are using. So we're going to be using 30 milliliters of the 20% saline bag. So great. Now we need to determine what our y value is going to be. And we can use either of our two original equations to help us out with that. I'm going to use our first one because it doesn't have decimals and it doesn't have gross numbers in that. So writing out our first equation. Oof. What is the splat word doing to me? There we go. Sorry about that. Bring this in here. There we go. Okay. So using what we've learned about our x value, and plug it into our first equation. So our first equation is written as the amount of 20% plus the amount of 4% is going to equal 40 milliliters. We know x to be 30. Subtract 30 from both sides. Find out y is equal to 10. So how much of each saline type are we going to be using? We're going to have 30 milliliters of the 20%. Trying to get this all in here in one picture. Don't know if it's going to work as well. We have 30 milliliters. Come on. We have 30 milliliters of the 20% bag, and we're going to use 10 milliliters of the 4% bag. That's going to give us our desired outcome here. And that's we go through and solve a mixture problem when we are specifically working with percentages and concentrations. So I know we've had mixture problems in the past where we are working with mixing amounts of coins together, where our setup was very similar, at least with our tables, but when we went to create our equations that we have here, we had to do that a little bit differently. So the setup is very similar, but when we make equations, we're working with something different now. So you have to make sure that we are being very, very careful as we are setting up and creating these equations for ourselves. Primarily with the fact that my first equation in this problem is adding the total amount in milliliters together. And my second equation is dealing specifically with the concentration of the first, second, and total amounts that are going to be saline. So 20% of the first thing plus 4% of the second thing is going to give me the 16% of the 40 that's going to be saline for my final answer. So again, concentrations versus amounts or values or anything like that. So do not rush this process as you are trying to determine both of these equations, because this is not exactly the easiest thing to get figured out there. If you need that extra time to do it, take that extra time if you need to. Okay. So I'm looking at our time, And where are our problems? The ones that we have here. Okay, we still have 3 more to go through, and I don't really want to rush our process for number 2, 3, or 4. Right here. So I'm going to call it there for today. We are not done with this section of material, but I don't want to have to rush through our second, third, and fourth examples, because again, story problems, I want to give them the just full time that they need. So I will end our recording here for today. I'll take any questions that you guys have, but we are not done with this, and we'll go through more examples of this tomorrow as well. So we'll end it here, and then we'll go from there.